just totally into it. Thanks, In-House DJs. We're going to talk today about Newton's laws of motion.
So, Newton's laws of motion are, of course, named after Sir Isaac Motion.
Yes.
Yeah.
No.
Psych!
Sir Isaac Newton.
The Fig Newton guy.
He's a very famous scientist, and in fact, he actually invented calculus.
And Fig Newton.
But don't hate him for
Not
that,
Fig
because
Newton.
he was also brilliant at figuring out how the universe moves, and he came up with 3 laws that describe it.
Yep. Yeah, so that's what these laws are. There's 3 of them.
We'll go
Describes
over them
how
in
things
greater
move.
detail in class. The first one, guys, Newton's first law, and it says the velocity. Right now, we could sort of think of that as speed, but we'll clarify what that is actually in class. But we can say the velocity of an object remains constant unless the body is acted upon by an external force. So what it means is however it's moving, it will continue to stay that way unless another force interacts with it. Could slow it down, could speed it up, could knock it around, could do all kinds of things, change its direction.
When it says body, does that mean my body? Or
It means any physical mass.
Oh, anything made of matter?
Anything made of matter. Doesn't matter if it's a car or a cupcake or a pencil or
What
a
if it's
racehorse.
not moving yet?
Doesn't matter. If it's not moving, then if something interacts with it with sufficient force, it will start it moving.
Gotcha.
If it's already moving, you can deflect it, like hitting a baseball thrown at you. You can hit it back or kicking a soccer ball. You're changing directions. Anything that's moving, these 3 laws apply to it. Doesn't
Okay.
matter. And anything that's not moving but has the potential to move, these 3 laws also apply. So pretty much
Cool.
everything in the world is affected by these.
And the universe.
And the universe. Yeah, I said the world. That's way too small. The universe, everything. To let you guys know, we talked about this first law here, but I want you guys to pay attention to it. It says inertia is a big term we're going to talk about. Inertia is resistance to change.
Yep.
Now that means if it's sitting still, the object tends to want to sit still or will remain sitting still unless another force acts on it. If it's moving, it's going to tend to move in that direction unless something happens to change its velocity or another force hits it.
Which is why a lot of times we say that Newton's first law is a body in motion will stay in motion and a
Yeah.
body at rest will stay
Will
at
stay
rest.
at rest,
Unless
yeah.
acted on by an outside force.
Exactly. So however they
Awesome.
are, they're going to stay unless something else acts on them. We'll talk about friction and forces later.
Yeah.
Right now, you guys, force, there's some terms we need to know. The first one's force. Force is the push or pull on an object. So it's either pulling an object towards something or pushing it away from something, but it's a force acting on it. Again, as we said, inertia is resistance to change. That does not mean resistance to move. If it's moving, it's going to want to keep moving until inertia overcomes it and makes it change, slow down, do something else.
And an easy example would be like a rock sitting on a cliff.
Yep.
It's going to sit there until something pushes on it.
Just like we had
Right.
potential energy, kinetic energy when it's moving.
Exactly.
It's almost like this stuff is all related.
Yeah.
Right. So then you got Newton's second law. Newton's second law is all about once the object's actually moving, how's it going to get faster or slower or whatever is going to happen with it. So the general idea of this is that the acceleration of an object is parallel, meaning that it's going in the same direction, directly proportional to the net force and inversely proportional to the mass.
That sounds complicated.
Which, if you look, we got 2 ways of looking at it. You have acceleration is equal to force divided by mass. So you take the force that's acting on an object divided by its mass, and you can figure out how quickly it's speeding up or how quickly it's slowing down.
Oh, okay.
You might want to write that down.
Yeah.
And then the other one is, if you know the mass and the acceleration, you can figure out how much force has been applied to the object.
Just by multiplying them, right?
Exactly.
So that's at F equals ma. I would write
Yep.
that down too. Both these
Definitely.
formulas are important, guys. Let's write them down so we can work on them.
So
And
this law basically boils down to the math, though.
Right.
Right.
This is basically the math
The
part of it.
wording there is like Sir Isaac Newton's wording, but really it's just him describing an equation to
That he
figure out
came
how to
up with.
calculate
Yeah,
force. or
figure out
such.
acceleration, force, and mass.
And we-
if you've got 2, you can figure out the third.
Yep. And we typically, when we talk about Newton's second law, a lot of times people just say force equals mass times acceleration. That's a lot of people just describe that law
Yep.
because it's just easier.
Because it really is. It
Although
boils
truly
down.
he actually described it as that first equation.
Yeah, acceleration
True, he
equals
did.
force
Yeah.
He did.
divided by mass.
But
But
we've
we've
changed
switched
it
it.
around the way we like to talk about it. So,
Yep.
so here's some. You could keep going on this.
Yeah,
you know?
well, I was just going to say the second law has there's a couple conceptual things that go along with this where you don't even need to do any math with it. So one of the things that goes with the second law is that an increase in force will lead to an increase or decrease in acceleration. What do you guys
F
think?
equals mass times acceleration. So if you increase...
Well, I'm guessing if I shove you not very hard, that's a small acceleration. If I
Yeah.
shove you really hard,
Yeah. We should
there'll be
do that
a
repeatedly.
greater acceleration.
Yeah.
Right.
So there's an increase.
Goes up.
So as force goes up, acceleration goes up. Makes sense. If
They're directly related to each other.
Yeah.
You increase acceleration, the force has to also
you
increase.
put more force in the ground, you run faster.
And then the opposite is
Sorry
if
for
you
pushing
decrease.
you.
That's all right. I don't care. If you decrease the force that you apply to something, then obviously you're going to then decrease the acceleration.
So they go
Right.
up and down together.
They're
Direct
tied to each
relationship.
other, directly related. Yep.
Neat.
Now, if you look at it in terms of mass, an increase in mass will lead to
That's a decrease.
an increase
No,
in the amount of force
decrease.
needed.
I'm sorry.
And the way to think of it is
Working
like
on my
this: if you've
muscles.
got a little teeny tiny like ping pong ball, it doesn't really take a lot of force to get it to go.
Nope.
But if you take like a giant like car, it takes a lot more force to get that car to move.
That's what I was
So it's got to increase. And then opposite is if you decrease the mass, then you decrease the amount of force.
So the lighter, the less mass something has, if you want to think of it in
Yep,
terms
easier
of
it is to
weight,
get going.
here on Earth, the easier it is to get it
Yep.
going.
Which is why they want to try to get cars to be as light as they possibly.
That's why they
Right.
don't have you kick bowling balls in soccer.
True. And then the greater the mass of an object, the greater the force needed. They all kind of just go together.
Yep.
So if you really think about it for force, if you increase the mass, you got to increase the force. If you increase the acceleration, you're also increasing the force. They're
Right.
all kind of
We'll work
directly
on this in
related to each other.
class. Let's think about things kind
Yep.
of logically. Like if
Yeah.
it's heavier, it's harder to move, that kind of thing. If it's
Exactly.
moving at you and it's heavy, it's probably harder to stop.
Right. All right, Newton's third law is for every action, there's an equal and opposite reaction.
No way.
Yes, watch. Ugh.
Right, so if you observed there,
Stop pushing.
when Mr. Harkins
Jerks.
pushed Mr. Black,
Man, you guys are bullies.
Mr. Harkins didn't just stay still and, stay
Yeah.
stationary as Mr. Black moved that way. Mr. Harkins also moved back. That's because when a force is applied, a force in the opposite direction
Yep.
Yeah.
always comes
So
back.
even though it didn't look like it, I pushed Mr. Black, but actually his mass pushed me back too.
Mhm.
That's the only reason we bring you in is just for demos. You're
Here's-
like a crash test dummy.
Here's kind of an
Okay.
abstract example, but also very important. Hey, Mr. Black, why aren't you falling through the floor right now?
I have no idea.
I do.
Why isn't Mr. Black
Because
falling through the floor?
he's pushing down on the floor with a certain
Magic.
amount of force.
Mr. Jansen, please dial the operator.
Mr. Janzik better dial the operator. Anyway,
It's
go
an
ahead.
emergency. And the floor is pushing back up on Mr. Black.
Right,
And
so you
those-
say
those
there's an equal
opposing
reaction.
forces keep them in place because they're equal.
So there's an equal reaction going up while your force on the ground is going
Yep.
down. So
Gotcha.
equal
Hope
reactions.
that never stops.
And if the pushing up force wasn't as strong as my force pushing down, then I
You would sink down, like if you're on water or in quicksand or in beach sand or on anything
Cool.
like that. You bloop, 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 bloop.
Makes sense.
This is why, when you jump off a boat or something, the boat moves. If
The
you
boat
jump
moves
that
away
way, the
and you
boat
go
moves
that
that
way.
way. Yeah.
Yep.
Cool.
So anyway, that is actually it. So
Go
see you
do
later.
your checkpoint, guys. It's worth it. Rock on.
Woo, Newton.
See ya.